Okay, welcome back, everybody. So I just put in the text a little recommendation for a book on data visualization. And this is primarily focused, you don't have to be an R user, but a lot of the code or all of the code is in R. But there's some great inspiration for a lot of different nice graphical techniques for you. And I just put the title and the author in the chat for you. And if you want to talk more about it, you can always send me an email as well. I'll give you my information at the end of the course. But just wanted to let you know that I, after taking a webinar through a STAT conference in the fall, got this, and I've just been using it a lot, and it's been a lot of fun trying some of the techniques that they have in there. Okay, so we'll keep moving along with some more graphical approaches and ideas that we want to keep in mind, and also the summary statistics that we've been looking at. Okay, so let me share my screen once again. Okay, that look okay, Emily? Okay, thank you. I'm always worried it won't. Okay, so just a reminder, we're looking at these birth counts per 100,000 people, county by county. So each dot is a county. And we looked at comparing these dot plots by region and making them into box plots. And so that we could kind of understand how they're related and how they're different. And some of the things that we need to keep in mind when looking at summary statistics, being wary of using the mean, especially in the presence of outliers. And if there are outliers, you can always report both the mean and the median, and the IQR and the standard deviation if you really still want to include the mean. Okay, so then we also have time plots, and these are simply displaying a quantitative variable over time. So they look at the relationship between a quantitative variable and time. And so what I did for this variable, and it'd be interesting to get your take on what you all think about this, being public health experts yourself. So I just took the sum of the births each year and just looked at the overall Montana births for the data, for these Montana IBIS data. And so we see this, kind of this upward trend up until 2008, and then we have a dip, and then it comes back in 2015. And then we have this dive, which it was a little surprising to me. And then of course, this is 2019 right here. And I will say that there are a couple of counties that are, I think just due to sensitivity, that once the population gets small enough, due to sensitivity, they won't report publicly some of the outcomes. There were a couple of years where there were missing counties, which that could be contributing to this. But time plots are excellent for detecting, we're all about detecting trends when we're looking at time plots. So things like, are there specific things happening when we see these fluctuations? Are we looking for, do we see an overall upward trend, an overall downward trend? Are we detecting any cyclical behavior? A lot of times we'll see the cyclical behavior, say, in air pollution over a year, right? A lot of time, especially in different communities that tend to be impacted by wildfire smoke or inversion type situations like we are here in Missoula, we'll see these annual cyclical patterns in particulate matter and other pollutants as well. So time plots can be really beneficial for detecting lots of different trends, tendencies, cyclical behavior, and so on. Okay, but what can go wrong with graphs? So, you know, I think that especially as long as we're using these statistical softwares and that we're educated, I think the biggest thing is just being educated about what's being presented and making sure that you agree with what is being plotted and double checking everything in your data. But you just want to, oh yeah.
I'm just going to interrupt you real fast. There was a question, did the overall population stay the same over that time period? Did it increase or decrease? And what about the population of women of childbearing age?
Those are all, yeah, those are all great questions. And I did not look at, those would definitely be my next step. And I thought about that as well, as figuring out getting data for, yeah, the age distribution over time, which of course would be affecting that. I guess I was just, I'm certainly that could be the main effect of what we're seeing, right? But I was just kind of surprised to just see that change, especially with some of the other data that I've looked at, and I just haven't had time to dive deeper. But that's a really good point, is diving a little deeper and figuring out some of the demographics over county and overall the counties that I can still get from some census data. And I don't know if IBIS has age distributions. I'm just getting familiar with those, but if anybody has any thoughts on other places, but I've been getting my age distributions, you know, you can't get extremely specific, but I can get age categories through the American Community Survey by county and by census tract. And so that would certainly be the next thing to look at from my perspective.
This is Silvana again. I put it in the chat, but so IBIS does have really good population estimates, and their NCHS population estimates, and for smaller states, they're more accurate than either ACS or census data. So if you're using any like population estimates, I would go there. And they do have, sorry, they do have like age interval breakdowns.
Oh, great. Mm-hmm. Oh, and so you would say that they're more reliable than ACS.
Yep. Okay. Yep. There's an additional weighting that goes on for population size with the NCHS data.
Okay. Great. Thank you.
Sure.
Okay, so just a few things to keep in mind. You know, just a lot of times people will like to use these like 3D effects and graphs, and that's fine if you really want to make something pop. And I understand that there's this fine line between making something exciting to look at, but then you also don't want it to be misleading. So for example, these cone charts that come from Excel, you know, D is supposed to have a height of 8. And that's really hard to see from this kind of like this 3D effect that they're trying to go for here, to understand, you know, this point lines up with this 8, but then this line back here doesn't line up with the 8. So it's just really hard to really just get, you know, it's a very simple distribution, and to be able to understand where those heights are really supposed to be falling. So, you know, you just want to come up with displays that actually represent your data. Something like this as well is just very jumbled and really hard to discern, you know, what some of the heights are when you have this 3-dimensional effect. And there are other ways that you could certainly display these data in a more effective way without the 3-dimensional effect, that you'd be able to see the relationships much more readily. This is an article published in Mother Earth News looking at different types of foods. You know, we've got fresh produce, cereals, and then they're trying to show the breakdown of these different types of ingredients. So super creative. They're trying to make it look like a grocery store, which I really appreciate. But in general, it's really hard for our eye to really understand the trend of what's trying to be displayed here. So this is a great creative graphic, but I would just say that, you know, when you're trying to do things like this, just be aware of trying to keep the balance of being creative, but yet still getting your data across. You know, there's a lot of things that just you don't know that when the different, you know, aisles are at different angles and the aisles aren't the same size up here. It's just hard to really know how to consume that with your eye. So just be careful, but also, you know, of course, be creative. So this is Hans Rosling. This is one of my absolute favorite videos. I was introduced to a documentary on some of his work when I was in graduate school. And so I just want to share it with you. It's a little bit dated, but I hope you'll appreciate it. And it hopefully will give you a little bit of excitement for trying to better communicate our data in a way that is approachable and exciting for the community to consume. So I'll share this with you. It's about 4 minutes long. And so I hope, and I just realized that I don't think I did the sharing properly to be able to do what I need to do here. Let's see here. I might need a refresher on what I need to do, Emily. Let's see here. So I go, oh, I got it. Okay.
Yep.
I got it. Thank you. Okay, here we go.
Visualization is right at the heart of my own work too. I teach global health. And I know having the data is not enough. I have to show it in ways people both enjoy and understand. Now, I'm going to try something I've never done before. Animating the data in real space, with a bit of technical assistance from the crew.
So, here we go. First, an axis for health, life expectancy, from 25 years to 75 years. And down here, an axis for wealth, income per person, $400,000, $4,000, and $40,000. So down here is poor and sick, and up here is rich and healthy. Now, I'm going to show you the world 200 years ago, in 1810. Here come all the countries. Europe brown, Asia red, Middle East green, Africa south of Sahara blue, and the Americas yellow. And the size of the country bubble showed the size of the population. And in 1810, it was pretty crowded down there, wasn't it? All countries were sick and poor. Life expectancy were below 40 in all countries. And only UK and the Netherlands were slightly better off, but not much. And now, why start the world? The Industrial Revolution makes countries in Europe and elsewhere move away from the rest. But the colonized countries in Asia and Africa, they are stuck down there. And eventually, the Western countries get healthier and healthier. And now we slow down to show the impact of the First World War and the Spanish flu epidemic. What a catastrophe! And now I speed up through the 1920s and the 1930s. And in spite of the Great Depression, Western countries forge on towards greater wealth and health. Japan and some others try to follow, but most countries stay down here. Now, after the tragedies of the Second World War, we stop a bit to look at the world in 1948. 1948 was a great year. The war was over, Sweden topped the medal table at the Winter Olympics, and I was born. But the differences between the countries of the world was wider than ever. United States was in the front, Japan was catching up. Brazil was way behind, Iran was getting a little richer from oil, but still had short lives. And the Asian giants, China, India, Pakistan, Bangladesh and Indonesia, they were still poor and sick down here. But look what is about to happen. Here we go again. In my lifetime, former colonies gained independence, and then finally they started to get healthier and healthier and healthier. And in the 1970s, then countries in Asia and Latin America started to catch up with the Western countries. They became the emerging economies. Some in Africa follows. Some Africans were stuck in civil war and others hit by HIV. And now we can see the world today in the most up-to-date statistics. Most people today live in the middle, but there are huge differences at the same time between the best of countries and the worst of countries. And there are also huge inequalities within countries. These bubbles show country averages, but I can split them. Take China, I can split it into provinces. There goes Shanghai. It has the same wealth and health as Italy today. And there is the poor inland province Guizhou. It is like Pakistan. And if I split it further, the rural parts are like Ghana in Africa.
And yet, despite the enormous disparities today, we have seen 200 years of remarkable progress. That huge historical gap between the West and the rest is now closing. We have become an entirely new converging world. And I see a clear trend into the future. With aid, trade, green technology and peace, it's fully possible that everyone can make it to the healthy, wealthy corner.
Well, what you just seen in the last few minutes is a story of 200 countries shown over 200 years and beyond. It involved plotting of 120,000 numbers. Pretty neat, huh?
All right, thank you. I hope you enjoyed that. He's just such a joy to watch, and so creative and excited about sharing statistics and public health. So I just thought that was a really nice way of starting to collect and summarize what we have done here. And it might be worth, or it might be a nice exercise for that video for you to just try and conceptualize or think about how you would organize and store and think about all the different variables that were just displayed in that data set that he provided. So he had year by year data, and all of those different variables that he was able to display on a single plot is pretty remarkable. But also just thinking about how you would organize the data in a data sheet, and just what that would look like in a long, tidy form. Okay, so final considerations when summarizing your data and writing a report with EDA. So a lot of what we call EDA is exploratory data analysis. So this refers to just this initial pass on your data that involves creating summary statistics, making some graphs, just getting your hands dirty and better understanding the basic relationships and distributions that you have in your data, outliers, missing values. These are all really important pieces. And then you can build a small report so that you have that saved, and then you can go on to future analyses or designing a new study based on old data, those types of things. But the final things that you want to think about when you're summarizing your data and writing a report. So it's really important to know, how were these data collected? So just like we had questions about the IBIS data, were these data collected on a mother's county of, or the county of residence, or where the birth actually happened? How are they actually calculated? How are they actually, how are those data actually recorded? Are they based on health records? Those are really important things that will impact the types of conclusions that you make. So making sure that you document those and understand what possible sources of bias there might be. So again, especially with rural areas that might be harder to reach and understand these birth outcomes, what are potential impacts on the conclusions that we're making, based on where the data are coming from, how they're collected, and so on. Those are really important parts of these summaries that we're making. We want to always be clear, organized, and fully explain what each graph or summary means. You know, whether it's for the future Cindy coming back to my report in 2 weeks, or to disseminate information to, you know, public, you know, members of the community or colleagues, you know, just making sure to be clear, organized, and having everything labeled. So it's, you know, and especially if you've ended up having to remove data or delete it temporarily just for visualization purposes, making sure to document all of that. And I don't know if I really focused on that much in the data cleaning aspect, but a lot of times, you know, we're forced to make decisions in the data cleaning stage and the data organization stage, such as variables that, or values that look like they were entered incorrectly, or different decisions that we have to make. And we want to always make sure to fully document those, so that that we know what happened or what changes were made in the data. And that can be done if you're doing R. That's really nice to just do within the code, or you can just create a document that shows how those changes have been made. But you always want to make sure to document that. And then just be really conscious, especially when you have data that are sensitive, you know, just always making sure to follow what protocol you have agreed, the data sharing use agreement, just being really conscious about, you know, if you're displaying data at the county level and it's a very low population county, you know, you might end up sharing data that are sensitive. So you just want to be really careful about that and paying attention to all of those privacy concerns. Okay, so that is the section that I had prepared for you on graphical displays and basic summary statistics. And those are all assuming that you have the those are all assuming that you have the data in hand. So now we're going to take a step back and think about, well, how can I best collect my data so that they represent what I'm trying to study, meet what goals I'm trying to fulfill. And the two main things that I want to talk to you about are sample studies, where you're trying to figure out how to best sample people or objects from a population, and then move on into actually conducting studies, which are called observational studies, where you're looking at relationships between different variables, or looking at experiments where you're actually implementing some type of a variable on, you're actually, you know, imposing a variable on someone, and then, or something, and then measuring the outcome. So we're going to look at those, kind of take a step back and look at the different ways in which we can collect data. Again, please don't hesitate to send me a chat, or send a chat to the whole group if you have a question as we go through these. Okay. Okay, so formulating a research question is...
Make sure you're in full presentation mode. The little screen button at the bottom.
Am I not? While I am on my other side, I think I might have shared the wrong screen.
Oh, gotcha. I look at it like if you were editing it.
Let's see. Okay, tell me now if this is better. Is it still not?
It's still loading. Okay. Hold on. There we go.
Thank you. I appreciate it. Let me know. It's been a whole year on Zoom and I still, you know, Okay, so formulating a research question. So I love this idea of like building a house without precise construction plans. You know, I think a lot of times we just dive in and we want to start collecting as many variables as possible because it just seems like the right thing to do without really sitting down and thinking about what are all of the factors that could be affecting my outcome. You know, what in the end is going to allow me to make the conclusions and study the problem that I really want to better understand. And so those just boil down to things that we've learned, you know, growing up, asking those W's and H's, you know, like who are we trying to learn about? What age group, where do they live? What's their gender, etc. How am I going to modify whatever it is that I'm interested in studying? For example, what if I want to know if the adherence to a Mediterranean diet can prevent heart disease? Well, how am I going to define Mediterranean diet? How am I going to impose that and or not impose that on some of my group and impose it on other parts of my group? If I want to know that it's going to, whether or not that diet is going to prevent heart disease, how is that going to be assessed? How am I going to define heart disease? How is it going to be, how are these people going to be as comparable as possible so that I can confidently make the conclusions that that I'm hoping to, and make an inference on the population I'm interested in studying. So this formulating the research question and then putting that into practice is a large art form, and it takes a lot of thought and work and research into being able to design a study that will actually allow you to answer the questions that you're interested in. So after looking at this, we might think, gosh, that's a lot to consume here. Mediterranean diet, heart disease. So then we might pare that down a little bit, and we might say, does an introduction of fresh nuts and oils combined with a, you know, quote, healthy diet, however we define that, reduce the incidence of major cardiovascular events in people who are at high risk? So that's a little bit more precise of a question, which we can then use a little bit more readily to translate into an actual study that we might want to design. Not that we're going to be necessarily going to be designing these, you know, intense clinical trials, but you kind of get the idea, hopefully, of what I'm trying to go for, of like being very specific about the population you want to study and what outcome you're interested in. Is there a question? Oh, okay. So we have this idea of sampling, where they're in all of the different things that we want to look at, we are going to incorporate randomness into our procedures. And there are different reasons that we want to incorporate randomness. There's a great website called random.org where they generate random numbers for you from atmospheric noise and help you design experiments if you like with random numbers. But in sampling, we're going to use it so that we can select individuals at random to help prevent selection bias and try and get a representative sample from our population. In experimental design, we're going to randomly assign different people to our treatment groups so that we don't let them choose their treatment, so that their choice is actually could potentially be a confounding variable that could actually cause any difference that we see. So we want to randomly assign them to treatments so that the only reason for the difference we might observe in their health outcome will be likely due to the treatment assignment itself. In statistical inference, we use randomness to better understand this notion of just the statistical significance. And we use it a lot to help us better understand p-values. It's at the heart of what a sampling distribution actually represents. even though it's a theoretical distribution. We use it for simulation studies. So bottom line, and I can talk a lot more, there's a lot of examples of why it's so important to use randomization. But just bottom line, whenever possible, whether it's in a sampling plan, an observational study, you want to try and include randomness in your study to prevent sources of unknown bias. That's the bottom line. And we'll see some examples of this. And I'm just gonna go fairly quickly, but I just want to show you a couple of examples so you get the main idea. I think we all probably understand this main idea of sampling, but just as a review and just to highlight a couple of the main types of study or types of sampling techniques. Let's suppose that this whole square represents a population. So maybe it's all Montana residents, or maybe it's all Missoula residents, some big population who we want to learn more about, okay? And we never know the overall big population picture, right? We never know the overall population quantities. But since we're just setting this hypothetical stage, let's say that we know, we have these 3 characteristics. We have pluses, circles, and stars. So you could associate this with any population characteristic that you want to impose on them. But in this population, there are 50% pluses, 33% circles, and 16.7% stars, okay? That's the population quantity, okay? So we never actually know the population quantity, but that's just for this is just for our purposes. Now, the idea of sampling is that, well, I cannot afford the time or the effort it's going to take, yet it's not even feasible to census this whole population, okay? Well, this hypothetical one I could, but in the grand scheme of things, I can't afford to go and census the entire state just to find out an answer to my question. So what I'm gonna do is I'm gonna take a simple random sample where every single collection of these individuals has the same chance of getting selected. Maybe I assign them a random number and then just basically, for lack of a better term, just like pick their number out of a hat, right? But we can use a computer to do that for us. And so when I do that, when I randomly sample 10, I get 60% pluses, 30% circles, and 10% stars. So compare this with the population quantity. So 60 versus 50. So my estimate would be that there are 60% pluses instead of 50. My estimate would be that there are 30% circles instead of 33%. My estimate would be that there are 10% stars versus a 16.7% stars, okay? But that is, in terms of our definition of statistical terms, these down here are what we would call population quantities or population parameters. Okay, they're actual values that represent the population. These are sample statistics. They're values that are based on a sample. And the whole goal of all of statistics is that we want to try and get learn about the population by taking a small sample. And so our whole life is all about, well, how much can we learn from these statistics here about the bigger picture, since we don't actually know what the bigger picture looks like. And that's the goal that we have, is learning about the whole population. Okay, so parameters represent a population, statistics represent a sample. And our world is all about better understanding what we call sampling variability. So in practice, we take a single random sample from our population and we make inferences based on that sample. But then we say, but if we could take another sample of size 10, and then another one and another one, how would those vary from sample to sample? So I conducted a simulation for us. In the first simulation, I got 6 pluses, 1 circle, 3 stars. The next one, I got the same. Then on the third simulation, I got 5 pluses, 4 circles, and 1 star. And then I got 7 pluses, 2 circles, and 1 star. So you kind of get the idea. And this is the idea of sampling variability. This is just due to random chance, how much I would expect these values to vary from sample to sample. And that's the notion of sampling variability. And it can be a little bit difficult to sometimes understand that concept. But when you think about, we're going to talk about this a lot here in the next few minutes, but when you think about when people say, well, what's your error estimate? If I say, well, 30% of people approve of this, you know, of this bill, plus or minus 5%, that plus or minus 5% is based on our knowledge of sampling variability. So they're acknowledging that that value isn't perfect, but they think that based on what we know about random sampling variability, that it's plus or minus 5%. Okay, and that's a lot of what we do in sampling and parameter estimates, is I'm trying to quantify what that sampling variability is going to be. Okay. So again, here's my simulation. And I plotted all of the sample proportions for the plus symbol, just so you can see that there's quite a bit of fluctuation. They ranged from 30% all the way up to 80%. Okay, but they're centered at pretty close to that population quantity of 50%. Okay, so but they're going back and forth on both sides of that true population quantity, 50%. Which is what we would expect. And, you know, of course, a sample size of 10 is quite small. So the smaller a sample size, the more fluctuation we would expect, because there's just more chances for larger amounts of sampling variability. Okay, but they do still seem to be centered close to that population quantity of 50%. Okay. So using the same data, then I created a population of 60 people with 50 plus symbols and simulated 200 different random samples of size 10 and created another dot plot. And you see that they are centered at that 50%, where I'm randomly sampling 10 people from a population of 200. You see that this looks like a kind of like a bell curve. And there's no, that's what we would expect to see. Okay, we would expect those sampling distributions to be approximately bell curved or normal in shape. They're centered at that true population proportion as well. Okay, so here are this big theorem. This central limit theorem is arguably like the biggest theorem in all of statistics. It's the central limit theorem, and it's what all of our most of our statistical tests and confidence intervals are based on, is this idea that a sampling distribution basically has this bell curve shape or a normal shape. It's centered at that true population proportion. It has less variability as the sample size increases, so that sample size allows us to quantify how much error to attach to our estimates, and it has a specific formula to it as well that we won't get into today. And so, but this theorem ends up being at the heart of everything that we do, and I'll show you some of this in the last section, but it's just important to know that this idea of sampling variability is a really important concept, and that it's at the heart of the rest of what we're talking about, and at the heart of a lot of statistics and understanding significance and confidence intervals. Okay, so back to our sampling plan. I just wanted to talk about sampling variability really quickly, because I think it's really important to note. So back to our sampling problem, this is a simple random sample, but notice that if these people are spatially located, notice that this whole area down here is not being represented in the sample. So if this is, you know, all of Helena, and we have a whole area in Helena that has no representation. So we want to make sure that we are able to get representation if this is a spatial location, or if there's something else that we already know there's a difference there, then we want to capitalize on that. Okay, and so the next thing we could do, if there's some separation of a population, maybe by gender, maybe by age, maybe there's, like, you know, countless possibilities. If we want to make sure that we're getting samples from each group, then we can focus on that and force the sample to come from each group. So this is called, we still add randomness, but we force ourselves to get samples from each group that we want to make sure that we're getting representation from. So in this case, this is called a stratified random sample. Each of these are called strata. And I want to make sure that I'm sampling from each of these. So I randomly sample from within each group. So then I would get something that looks like this. I still take a sample of size 10, and I still get that, that sample statistic. So again, just like I said, spatial statistics, you could do a whole year, time series, a whole year of study. Sampling is the same thing. So then you could then adjust for maybe land area or population, things like that within your, when you're combining, you're pooling your proportions. But just if we take an overall proportion of pluses, this would be our new sample statistic. We would then, you know, just combine them all, 50% pluses, 30% circles, 20% stars. And so that would be the product of our, those would be our statistics from our new stratified random sample. But again, we could do some weighting depending on if there are differences in those strata that we need to account for. Another possibility is a systematic random sample, which is sometimes helpful if you don't have like a list of individuals that you want to sample from. You can just go down a transect and say sample every 6th object or 6th person, and this ends up usually giving pretty good coverage as well. But systematic, it just means you're systematically sampling every nth person you can use to get some coverage and representation from your population. Okay, so realistically, when this doesn't usually happen in practice, right? That I know what every individual in my population, and that every individual in my population that I try to capture, that they're actually gonna answer my survey or agree to be counted. So this is like best case scenario, that I know everyone in my population and I have control over who I count. There are a lot of potential sources of bias in sampling that we just need to be educated about and aware of. So for example, you know, we have these Gallup polls where they use random digit dialing to call people and ask them questions about all these different areas of interest in our country and our world. Okay, and so they call people and ask questions, but you know, with these calls, there's a lot of hang up. They're calling landlines and cell phones, so they have to adjust for that. And there's a lot of potential sources of bias here, but they design these surveys to try and minimize all of those. But so here's a headline on the Gallup website. It says, in the US, 14% with likely COVID-19 are going to avoid care due to cost. That's based on the sample that they took. Okay, and so let's just talk about, you know, this idea of what I want to define what's called a, so anyway, they said of all US adults, if you or a family member had a fever and a dry cough, would you avoid seeking treatment due to concerns about the cost of care? So so they have this overall proportion, 14% said yes if they just had a fever and dry cough, and then 9% said that they would, even if they suspected the coronavirus infection, that they would avoid care. And then they break it down by a few different demographics as well. Okay, in sampling, the sampling frame, we have the population of interest, that is this blue square here. And then we have the sampling frame, and those are the people that we actually have the chance of reaching. And a lot of times, so our goal is that the population of interest is exactly matches the sampling frame. So everyone who we're trying to reach in the population is the same set of people who we're hitting with our sampling frame, okay? But it could be that, you know, all of these people out here, they're never gonna answer the phone. They just will never answer the phone. They're unreachable by phone for these Gallup polls, okay? And so these people out here are never going to be captured in our information. And this is the trouble and the crux of a lot of our polling and sampling that we do, is that there could be a very discernible difference between these people and these people, or these objects and these objects, in terms of our outcome, and they can largely impact what our overall conclusions. Furthermore, with our sampling frame, we can also get people in our sample who aren't in the population of interest either. So we can, based on our sampling design, we could end up getting people who aren't even people we want in there, based on the research goals that we've outlined. And so we want to be conscious about understanding this in our conclusions, right? And in our sampling plan to begin with, when we're formulating our research question, so that we can work as hard as we can to make sure the sampling frame meets the population of interest. Let me know if there are any questions about that concept. But I like this diagram just to think about the importance of making sure that your plan is as dialed in as possible, so that you can actually make conclusions from your study. You know, because if your sampling frame is totally off from your population, it's really hard to, you can't, there are no magical statistical methods to overcome a biased sample. So we unfortunately don't have that. So we have to, you know, we have to design our studies so that they are well representing what the goals that we're trying to face. Okay. So Gallup conducted telephone interviews with a random sample of 1,017 adults living in the US between March 1st, and I'm sorry that got left out, but they attained a minimum quota of 70% cell phones and 30% landline respondents. So they have these quota samplings that's kind of similar to stratified sampling, where they want to make sure they're getting both cell phone and landline respondents. And then they looked for underrepresented groups, trying to weight them accordingly. So what is our population of interest in the sampling frame for the Gallup poll? And we don't need to enter just in interest of time, but let's go ahead and just think about for a minute what the population of interest is here. So if you're getting a random sample of US residents using cell phones and landline random digit dialing, what's your population of interest in your sampling frame? And what would be your population parameter of interest, if you can think about that? Maybe just think for a minute about that. And remember, they're asking people once they get them on the phone whether they would avoid going in for a health visit, even if they had COVID-19 symptoms. Okay, I think I'll thank you for thinking about that for a little bit. So these Gallup polls, they're really trying to get at, you know, in a perfect world, they would hit everyone in the United States. So they would say, they would call this blue square, say everyone in the United States. We want to know, basically they want to know if, you know, what proportion of people, if they suspected a coronavirus infection, what proportion would avoid seeking health treatment. And they got a 9% in their sample. So that's the population of interest is really all Americans, all US residents. That's the population. In reality, the people who they're going to get, the sampling frame is the people who have the chance of getting selected. So those are any people who have a cell phone, have a landline that can be reached using this random digit dialing. And you could even add in there that they would actually answer the phone from an unknown number, right? Like, which I probably, sometimes I do. But that's really who they're getting, are the people who have access to a phone and will answer the phone if dialed, right? And so that, you know, we probably don't have any overlapping here of people, but there's definitely a lot of people out here who are going to get left out. And so the big question that is in the polling world right now, because it's getting harder and harder to poll, is that, you know, what is different about these people who can't be reached for these polls, who just won't answer the phone, who don't have a phone? How different are they from this population who are participating? And that can be a really big gap. Put on top of that, like the sensitive questions, you know, if there are any questions that people don't want to answer, if they don't want to answer for certain reasons, if they don't want to answer honestly. Great, thank you. So the bonus question here was, what sampling plan most closely resembles what is described as above? So my goal was here to get you to think about, so we have the simple random sample, we had the stratified random sample, and then we had this systematic sample. And if we're separating people into cell phones and landlines, granted you could have both, but in terms of how people are being reached, that is kind of like a stratified sample, because you're putting them into two groups and then making sure you get 70% of the selection is from cell phones, then 30% from the landline. So that's kind of most similar. And then the overall population parameter of interest is the overall proportion of all US residents who would avoid coming into a clinic if they thought they had COVID-19. That's the goal. That's the big number that you want to know or learn about. So just going back to this idea of sampling variability, we're not going to go into a lot of detail, but this is the central limit theorem again kind of coming into play, where I did this simulation assuming that the true population proportion of people who would avoid medical care with COVID-19 is 15%. Just making that assumption. This is a simulation of all of the possible sample proportions we could get in a sample of 1,000 adults. Okay, so this is, remember, Gallup sampled 1,017 adults randomly. So I said with my computer, well, let's assume that, you know, let's assume that we are sampling 1,017 adults and that the true population proportion is 15%. What would all of those, if I sampled many, many times, just like we showed before, like a simulation, what would the distribution of all of those proportions look like? Well, here on the left, if I only sampled 500 people, I get sample proportions that range from 10% to 20%, but they're basically centered at that 15%, right? And that bell-shaped curve that we talked about. Now, if I increase my sample size to 1,017, just like the Gallup poll did, I now am still centered at 15%, but now the variability in my distribution has come in a little bit. Okay, and so if I wanted to give someone an idea of what I thought this value was, and I took a random sample and I got, say 0.153, then I would say, based on this idea of the central limit theorem that I have, I'm gonna add, 4 percentage points to either side to give you a general error to that. In this one, I might even do, so if I have 0.15, based on this simulation, I might even just add 3 percentage points. So I might say, okay, 15% of people who would avoid medical care is 15%. And then I would say plus or minus 3%. Okay, and that's that fluctuation on either side that I would give myself, that error. And that error comes from this idea of these simulated distributions. And I know this is a lot to take in, but if you can just get this idea of, as sample size increases, sampling variability decreases. So the bigger the sample size, the less error that I'm going to have. But the big kicker is that it has to be a good sample. A bad sample that has 1 million people in it is worthless, right? It still has to be random and representative of the population I'm trying to learn about. Okay, so, and there are other forms of bias. Some members of intended population have a lower or higher probability of being included in the sample. Response bias, is this a topic in which a respondent might be untruthfully answering or incorrectly answering? Or non-response bias, are the people who aren't responding to my survey different in some way? So these are all things that are really important when we're thinking about these sample surveys and potential sources of bias. And this is just a fun little graphic that displays this idea of, you could sample 1 million people, but have a very biased sample. Okay, so you can have a lot of precision, but have bias and be way off target, right? So that's not going to serve you very well. You can be, you can you can sample very few people and also be off. So that would be imprecise and biased. So you don't want to be off target there either. So these two are, the most concerning. You can be accurate, like honing in on the bullseye, but you can have a lot of variability. And that's what happens with low sample size, but yet you've designed your survey correctly, but you might not be able to make conclusions because you have so much variability that you're unable to really hone in on the target perfectly as well. And then you have this sweet spot where you have high precision and no bias. So you're hitting the target, you have enough, you have low sampling variability because your sample size is large enough and your sampling plan is great. So this is where we really want to end up. And this is in a nutshell what the central limit theorem is telling us, is that if we have a large enough sample and it's unbiased, we've done our sampling correctly, then this is what is going to happen. And that's what we're hoping for. Are there any questions about that or anything I can elaborate on? Okay, so this is one of my favorite illustrations to share, because I think it's so easy to think that, if I'm studying Montana versus the United States, that my sample size has to be a lot bigger to study the United States versus if I'm only wanting to study Montana. And that's simply not true. And it's really counterintuitive, but I love this example to try and explain to you why that is. So how big does my sample size need to be? it's all about how much error you're willing to accept. So it's all based on that sampling distribution that we looked at, right? The bigger the sample size, the less sampling error you're going to have. But it has nothing to do with your population size, okay? So this is a common misconception. Larger population sizes require larger sample sizes. That's not true. Your sample size is based on how big of an error you're willing to accept. So for example, we have this pot of soup, you know, just at home on the stove, just for, you know, you and a couple of family members. And you're making this awesome soup. You've got all these great herbs and spices, and you take a small spoonful to test it. And you take a big enough spoonful to get everything in there, right? The broth, make sure everything is cooked properly. It needs to be a big enough spoonful so that you get all the ingredients in there and you know that it's done and how you want it to taste, okay? So big enough scoop out of this small pan to get a taste so that you know it's done. Well, then you're making this giant vat of soup for a huge family reunion, you know, COVID is in the dust, big gathering, but you need to test it to see if it's done, okay? So the whole analogy here is you don't take this giant bowl of soup and eat the whole thing just to test to see if it tastes okay, right? You still take the same size of spoon from the big vat that you do from the smaller pan, because it still gives you a sense of how the soup tastes, whether the beans, the rice, the veggies are done, okay? And that's the whole idea with sample size. Sample size is hugely important, but it has nothing to do with population size. So just keep that in mind, that it's all about how much error you're willing to accept. And that goes through when you start to do like power analyses for your studies, if you're designing a study. Then those are the things that you'll have to do, but it doesn't matter but about your population size. So in the grand scheme of things, big picture is we want to just design our studies as well as possible so that we can get a sample that's representative of our population, that's big enough to be able to make the conclusions that we want to be able to make with confidence intervals and hypothesis tests. And, you know, the big picture is really asking all of the tough questions first while you're designing your study, so you don't have to go scrambling and do another study to go back and make up for errors that you made, which is always going to happen anyway, but you try and minimize those, right? Plan ahead and thoroughly design your study so that you don't have to worry about errors and biases during the analyses. Okay. And then I'm going to talk to you a little bit about, so those are all sampling plans. And then my favorite is thinking about experiments and observational studies, which we will do now as well. Are there any questions about